All right, so today we're going to do Riemann sums. Everything's named after the guy that came up with it, so this guy Riemann. So what we're going to try to do is estimate the area under a curve. And so I picked an easy function for us to start with. So this is just f of x equals x squared. So just a regular old parabola. It's not transformed or anything, just your parent function for x squared. From 0 to 1. So it's just this part of the parabola. If we had drawn the whole thing, it would be like over here, but we're just going to concentrate on 0 to 1. And we're trying to estimate the area of this. Now, it's not an area that you can find exactly using like a geometric formula. It's not a perfect triangle. You know, we have an area formula for a triangle and so forth. So what we're going to do instead to estimate it is use these rectangles. Now what you're going to do is break the interval into sub-intervals. And for this first example we're going to go through, I did 4 sub-intervals. So we're going to find the areas of each of these 4 rectangles. And you're like, it looks like there's only 3, Miss Cole. The first one, and this is what I like to highlight so you can see the heights of the rectangles. The first one just has a height of nothing. Like this first sub-interval, we don't even end up getting a rectangle. And then for the second sub-interval, this is our height. And then this is your third sub-interval and your fourth sub-interval. That's giving us all the heights of the rectangles. And to get that height, you're going to plug that value into the function, which we said was x squared, because that's where it's hitting this graph. So if you plug 0 into x squared, you're just going to get 0. 0 squared is 0. That points on the origin. And this is from 0 to 1. And I broke the interval into fourths. There's 4 equal sub-intervals. So this is a fourth, a half, 3/4, and then 1. I know it's written there, but it's real small. I'm just writing it bigger. So if you plug a fourth into x squared, that's going to give you a 16th. If you plug a half into x squared, that will give you a fourth. And if you plug 3/4 into x squared, that's going to give you 9/16. All right, so we're going to find the areas of all 4 of those rectangles. A rectangle is base times height. So for this first one, base times height, that's going to be 1/4 times the height, which is 0. And then the next one, again, the base is going to be 1/4 for each of these because it's 4 equal sub-intervals. So this would be a fourth times a 16th for that height. And then the third one, we're finding this area here, this would be a fourth times a fourth. And then the last one is going to be a fourth times 9/16. And so what that's going to do is it's going to give us all of these areas. We're trying to estimate the area under the curve. Now, if all of the sub-intervals are an equal length, like if these are all uniform, you can get away with writing this in the factored version. So the sub-interval is a fourth for each of these. And then you can just write it as adding up these heights. So 0 plus a 16th plus a fourth plus 9/16. It's a shorter way to do it. You can only get away with that when these are all uniform. If all the sub-intervals are all different lengths, then you have to do them all individually. You can't get away with writing it like that. Now, for the sake of time, I have this answer written down. If you type this in the calculator, you are going to get 0.218. And what we just did is called a left Riemann sum. And the reason it is called a left sum is we used the left side of each of the sub-intervals to get the height. When we broke this down into our 4 sub-intervals, we used the left side of it to get the height. So hey guys, if we're trying to get the actual area underneath this graph, is this an underestimate or an overestimate? Yeah, good. It is definitely under. All these blank spots are area that we're missing, so this is definitely an underestimate. And so for a left sum, if the function is increasing, like this one is, it's going to be an underestimate. And if the function is decreasing, it's going to be an overestimate. Because if you think about like a function increasing like this, if you take the left side, that's the lower downside. If your function was decreasing, like if it was going like this, it was decreasing. If you're taking the left side of your subintervals, that's the higher up side. So that's going to give you an overestimate. So now we're going to repeat that process. This one, spoiler alert, this one's going to be a right Riemann sum. So if you want to highlight, we have the same function, the same 4 subintervals. This time, to get the heights of the rectangles, we're going to use the right side of the subinterval. So when you go to plug these into the function is still x squared. This is a 4th squared, that's a 16th. A half squared is a 4th. 3/4 squared is 9/16, and then 1 squared is 1. And again, the reason we're plugging those into the function, this is your x squared function, that's where they're hitting the graph. So that's giving us those distances. And again, since all these subintervals are uniform, they're all 1/4 in length, you can write this sort of this abbreviated or factored sort of version. You can take out the 1/4 and then just add up all the heights. So a 16th plus a 4th plus 9/16 plus 1. And for the sake of time here, I'd already typed that in. That one is 0.468. And I mean, there's more decimals. I'm just truncating it to 3 places. So hey guys, is that one an underestimate or an overestimate? Yes, way over. All of these extra parts that you're getting here are way over the graph. This is why, I feel like, and again, this is a personal opinion, I feel like integrals are easier to deal with than derivatives. They're very based on like concrete, tangible things like these areas, like that you can see and touch. Derivatives are, very abstract for the most part. Right, so this is an overestimate, and what we did is a right Riemann sum. And so if your function is increasing, like this one is, a right sum is going to be an overestimate. If your function is decreasing, then your right sum is going to be an underestimate. And it makes sense logically, like you can think about what it looks like. This graph is increasing, so if you take the right side, it's higher up. If you had a function that was decreasing like this, the right side is going to be lower down. You're going to end up with an underestimate. Right, so this next one, we are using what is halfway in between the interval to get the height. So this one is going to be called a midpoint sum because we are using what's halfway in between. So if this is 0 and this is a 4th, again, each subinterval is a 4th. So that, the base, when we do base times height, the base is still going to be a 4th for all of these. Halfway in between, this is going to be an 1/8. And then you can kind of just count by 8ths. This is 1/8, a 4th is 2/8. This one's 3/8. A half is 4/8. 5/8, 6/8, 7/8. And so those are the values that we're plugging into the function to get those heights that I highlighted. Again, the function is still x squared. I didn't change that. That's still this parabola. So if you plug in an 1/8, you're going to get 1/64. 3/8 is going to be 9/64. 5/8 is 25/64. So I'm just squaring all these, plugging them into x squared. And then this one is 49/64. So again, if we want to get this area, adding up all these rectangles, it is base times height. The base is still a 4th. For each of these, I kept it the same. So they're all still 1/4. And then you're just going to add up the heights. Again, it's like we've factored out that 1/4. But again, you can only get away with doing that if all the subintervals are uniform. If they are all different, you have to do them all individually. Here, I'm going to get to that. It's going to depend on the concavity, which is really hard to tell and hard to see. You're going to kind of just have to believe me, or I guess you can Google it if you want to. This one is going to equal, what did I have right now? 0.328. And this is obviously a much better estimation. The parts that are overhanging are kind of canceling out with the parts that are under. So it's a much better estimation. This is called a midpoint sum. And if your graph is, yeah, do you want to make a guess? I'll tell you what it is. If your graph is concave up, yeah, this one's really hard to tell. In fact, I can't. I'm telling you what the truth is because, you know, I've read it out of a book, but it's like almost impossible to tell. I'll tell you how I remember this once we do the last one. If your graph is concave up, it's going to be very slightly an underestimate. If your graph is concave down, it's going to be very slightly an overestimate. So since this graph is concave up, it's a parabola, so concave up, this is going to be a very slight underestimate. But yeah, that's really hard to tell. Oh, brackets instead of parentheses, it really doesn't matter. You can put parentheses. A bracket is really just like a parentheses older brother. I just use them when I'm bracketing off like a whole list of things because in my brain I feel like, oh, I'm bracketing this off. You can use parentheses. It really doesn't even matter. That's like that's because I'm weird. You know how I also capitalize all my trig functions? Like I'm the only one that does that. Or I don't know if I had a professor once that did that and I started doing it too. That's Miss Cole being weird. You can use parentheses. Or whatever floats. All right. And then the last one, we'll do this last one and then we'll do another break here. The last type of sum is going to be using trapezoids. And you can see this is a really good estimation because when you do these trapezoids, they're very, very close to the actual function. You need to know the area formula for a trapezoid. You will have to memorize this. It's not going to be given. It's 1/2 times the height, and then you add the bases together. All these trapezoids are on their sides. So when we look at these trapezoids, like look at this one, it's the biggest one, so it's the easiest one to look at. The height is going to be this distance, which is the length of the subinterval. So that's the height. And then these are the two bases, because all the trapezoids are on their sides here. All right, so I'm once again going to highlight here. And these are going to be the same numbers that we've found in all these other problems. This one's 0. This is a 4th squared, so a 16th. This is a 1/2 squared, so a 4th. This one's going to be 9/16, and then 1. So this one, I'm going to write it out the whole way, like do all 4 trapezoids separately, and then I'll show you the abbreviated version. Again, you can only do that like factored or abbreviated version if all of these subintervals are the same. So since all the subintervals are a 4th, that's the only reason you can get away with that. Right, but I'm going to do all 4 separately first, because if they're not the same, you have to do all the trapezoids separately. So we're going to use this formula. So it's going to be 1/2 times the height, which again is this. So that's a 4th. The height is going to be a 4th for every single one of these. And then you add the bases together. So for this first one, it's going to be 0 plus 16. Or I'm sorry, 1/16. I apologize. All right, plus. And then the next one's going to be 1/2 times 1/4. And so we're looking at this one now. So if I add these two bases together, it's a 16th plus a 4th. And then the third one, it's going to be 1/2 times the height, which is a 4th. So now I'm looking at this guy. So we're going to add these two bases together. So a 4th plus 9/16. And then the last one, once again, 1/2 times a 4th. And this is the last trapezoid we're looking at. So those two bases that I highlighted are 9/16 plus 1. So that's all 4 trapezoids separately. Now the way that you can abbreviate this, again, if all of the subintervals are the same, notice every single one of these has a 1/2, and then every single one of them has a 4th. So you can factor that part out. So I'm taking out that 1/2 that's just in the formula, and then the height, which is, again, the length of the subinterval, that's 1/4. And then we're going to add up all of these. But to write it in a little bit of an abbreviated version, notice you only use the 0 and the 1 once. So these ones on the end, those only get used once. But notice the 1/16 is in there twice. And then the 1/4 is in there twice. And then the 9/16 is in there twice. And the reason for that is they're shared between these trapezoids. Like the 1/16 is shared between the first and the second one. So it's going to be whatever your first base is, plus I'm going to double the next one, and then double the next one, and then double the next one, and then the last one is only once. So the ones on the ends only get used once. The ones in the middle get used twice because they're shared between each of the trapezoids. So that's a little bit shorter than this. And if you were to type that in a calculator, you're going to get 0.343. And again, more decimals, but I truncated it, so 0.343. And so, let me real quick right in here, the trapezoidal sum is the average of the left and right sums. So if you get the left sum and you get the right sum, and then you average them, so add them together and divide by 2, you're going to get this trapezoidal sum. And so the way you tell if this, well, let me ask you guys first, just from looking at these trapezoids are very slightly where. Is this going to be over or under? I know it's hard to tell because it's so close. Good, it is very, very slightly over. You have this tiny little bit that's overhang. Yeah, just a tad. It's a really good estimate. So very slightly overestimate. And this one also comes from the concavity. If your graph is concave up, it's going to be a really slight overestimate. Concave down is a really slight underestimate. And let me just draw one that's concave down for a second so you can see that as well. If you have a graph that's concave down, when you draw in the trapezoids, they're going to be like this. So they're going to be, really slightly under. So the way I remember the midpoint one, because I know this one's like almost impossible to tell just from looking at it, like left, right, and trapezoid, you can see this is very slightly under or very slightly over. So the way I remember the midpoint one is it's the opposite of the trapezoidal. Because the trapezoidal, I can always look at it and see. And so the way my brain does it is I'm like, oh, well, midpoint is the opposite of that. All right, so real quick to wrap this up. Are any of these estimates more accurate than others? Like, do you think some of them are better than others? Like, if you were trying to get the true area, is there one that you would pick? Yeah, and that's probably the one I would go with as well. Midpoint is 2, but that's a little bit more iffy because you have all this blank space. I think this is, probably best bet if you just had to, guess and do an estimation. But what could we do? Yeah, exactly. It might be more accurate, but it's harder to prove it. So I kind of go with trapezoidal. But what could we do to make the estimates more accurate? Like say I wanted to do a left sum, but I wanted this to be better. Like I didn't want to have as much blank space. What could I do to make the estimate better? Yeah, now if you average both left and right, that's just going to be a trapezoidal sum. I'm saying, say I wanted to do a left sum, but I wanted to make this left sum better. How could I have less blank space? Like, what could I do? Good, perfect. More subintervals. Let's say I did 8 subintervals instead. I'm not a very good drawer here, but like, say I did, I'm not going to be able to draw it in here. I can't draw it as well. But say you did 8 subintervals instead of 4, you would end up with less blank space in it. So the more subintervals you have, the better. It's more annoying because that takes longer to, write the whole thing out, but more subintervals is going to make the estimation more accurate.